welcome back. Man, I went way long on cyclones and anticyclones. I was planning about 20-25 minutes and it was longer than that. So let's move forward and start talking about how these features are related to jet streams here in the second part of our lecture. Let me give you a definition of a jet stream, and then we're going to see that we're going to pick this apart and be a little more specific about that. I mean, strictly speaking, in meteorology, a jet stream is any place in the atmosphere where the winds are stronger than the winds are right above that location, or right below the location, and right to the left of the flow, and right to the right of the flow. So, like, these winds right here are a local wind maximum. If you went higher than that, you're in weaker winds. If you went lower than that, you're in weaker winds. If you went to the right of that, you're in weaker winds. If you went to the left of that, you're in weaker winds. So it's just an area, a channel, a path where the winds are moving faster. The trouble with this basic definition that comes from like the glossary of meteorology type in textbooks and so on, is that lots of things meet that definition. I mean, there's plenty of things that we are interested in meteorology that would meet this definition, like so-called low-level jets, which happen at the top of the near the top of the boundary layer, and at night, or the African easterly jet, which is part of the monsoon in West Africa. But that's not what we're really talking about when we read this part of the textbook here. For our purposes and for what your textbook is doing, we're going to be a little more narrow than that and say, yes, all that stuff is true, but it also needs to be synoptic scale, which means it has to be at least, a couple hundred kilometers wide. This jet stream needs to be in the upper troposphere. We're not talking about stuff going on in the boundary layer or anything like that. We need to be like in the upper troposphere, almost to the tropopause. It needs to be flowing primarily in the east-west direction. It can meander north and south too, but primarily it has to be east-west, west-east. And it has to have waves in it. We're going to learn about these waves or these meanders in the jet stream that are going to be planetary scale in nature as well. Now, when you actually start working with a definition like that as to what you mean when you talk about a jet stream, you're going to start seeing maps that look something like this. Now, this is not my favorite map, but the colors on here, red means that that's the fastest winds at that particular time on this map. And, this is maybe 10 kilometers above the surface of the Earth, and you see that red path through there. That is a jet stream going from west to east in kind of a river of air. I hate the term river of air. Think of it more like the fast lane, okay? I mean, rivers have banks where the water isn't moving at all because there's no water. Think of it more like in many lines of traffic, this is the one that's moving faster, okay? So you see how there's that kind of channel there across the map where the flow is, going very fast. It's a jet stream. How fast are jet streams? In the range of maybe 150 to 200 miles per hour, something like that, on a really strong jet stream. You can see that this, certainly at least 100 miles an hour, you can see that this jet stream is a few hundred kilometers wide, but thousands of kilometers long. And in fact, once you have defined or limited jet streams to this kind of phenomenon, you'd see that in the northern hemisphere, there's two main jet streams. The one that's on that map that's kind of labeled as that blue wavy arrow going around the Earth at mid-latitudes or higher, that is called the Midlatitude Jet stream, except when we slip up and call it the Polar Jet stream, except when we slip up and call it the Jet, all of which are just synonyms. Okay. There's a second jet stream that's called the Subtropical Jet stream. That's the one that's kind of in that orangish color as it goes around the world. And it's at a lower latitude. It tends to be about maybe 30 degrees north or something like that. And it is a different phenomenon. It happens for different reasons. It doesn't affect the weather in, say, Omaha nearly as much as the mid-latitude jet stream does. Both of these jet streams, the subtropical jet stream and the mid-latitude jet stream, are westerlies. Remember, we always describe winds in terms of which way they're coming from. So a westerly wind means that they are from the west. If we focus for a little bit on the mid-latitude jet stream, one of them, which I have circled there kind of in red, one of the most important things to know about the mid-latitude jet stream is that the mid-latitude jet stream tends to be found more or less right on top of fronts. So like I've got a map here that I stole from the Weather Channel. See how there's like a cold front on that map there? The white arrows there are supposed to be the jet stream, and now the front's at the surface, and the jet stream is, 10, 11 kilometers up or something like that, but it's going to be more or less right on top of the front. There's actually good reasons for that. One of the most important rules in meteorology is the so-called thermal wind relationship. It's also the thermal wind equation, but we aren't ready yet for the actual equation and what to do with it and wind power and so on. So we're going to leave that kind of, put a bookmark in that. But the thermal wind relationship explains why there should be jet streams next to fronts and so on. And so the mid-latitude jet stream, that works. The subtropical jet stream is there for very different reasons that, again, we're not going to dwell on because they don't have anything to do with wind power. Now, all of these features of these jet streams here are going to be associated with features of the general circulation. Remember back in the lecture that was about why the wind blows, we learned about how the atmosphere is described by a 3-cell model that had a Hadley cell, and then we didn't actually even name the other ones, but there was these 3 circulation cells in the atmosphere. Turns out that the polar jet and the subtropical jet are kind of nestled into 2 little nooks and crannies of the general circulation. Exactly how they fit there and why and stuff, that's not the purpose of this class. But the idea that they are tied to the basics of how the atmosphere works is important. And I do want to introduce a little bit of notation that's going to be useful to us at various times through this semester. If you actually took a look at this diagram here, with the North Pole off to the left and the equator off to the south, we are looking, when we look into that map, we are looking east. So since the jet stream is going from west to east, the jet stream is like going into the screen right here. That is indicated, it's hard to draw vectors in 3 dimensions. To draw a vector that's going into the screen, the symbol is circle cross. See how I put circle crosses on there to help? It's like an X with a circle around it. Excuse me. Those are circle crosses that indicate that the wind is going into the screen there. If it were opposite, if this had been drawn in such a way that the wind was coming out of the screen, we'd have used circle dot. It's a circle with a dot in the middle. Okay, we'll review that notation the next time we need it here. But again, this, just to review here, these features of the general circulation, like the Hadley cell and subtropical highs and polar easterlies and all that, subtropical jets and mid-latitude jets are part of that story. Let me give you some adjectives that we use to describe jet streams. Jet streams can be either zonal or meridional. These are words that we can use to describe either the mid-latitude jet stream or the subtropical jet stream at different times. When a jet stream is described as being zonal, what we mean is that it mostly goes straight from west to east. If the jet stream is being described as being meridional, kind of the opposite. It is meandering to the north and the south as it heads from west to east. And probably the best way to help you see that is to look at 2 examples here. The globe that I'm showing there on the left has a jet stream indicated in red there, flowing from west to east, and I would describe that as being very zonal. Mostly the flow is going from west to east. Yeah, there's a little bit of wiggliness in it, but mostly the flow is zonal. In contrast, over there on that globe on the right, we see a jet stream that swings north and south. Okay, it's not going up and down, it's going north and south, it's meandering, and the right word for that is that we would describe this jet stream as being meridional at this time. Meridional comes from the word that means like following meridians, the north-south longitude lines. The origin of zonal is a much more complicated word, but I want to draw your attention to something weird on these maps. Wait a minute. Dr. Shragi, you told us that there were 2 jet streams. How come we're only, there should be a subtropical and a mid-latitude one. How come I'm only seeing one on each of these maps? Good point. That immediately caught my eye too, until I looked at the captions from the figures on the website that I got this. And these diagrams are showing the wind at a particular height, like 10 kilometers above the ground. Well, the subtropical jet stream tends to be higher above the ground than the mid-latitude jet stream or the polar jet stream. And so like that yellow line on there is supposed to be illustrating the height above the ground we're seeing the polar jet just fine, but the subtropical jet stream is higher than this. We're not actually even seeing it on these maps. Okay, at least it makes sense. All right, as to what's going on here. Let me give you some more vocabulary that helps you describe the jet streams that you're seeing. When we have the flow that is meridional in the jet stream, when it's swinging north and south in the form of these waves in there, one set of features that you'll form are troughs. And troughs are these sort of U-shaped features here on a map where the jet stream is headed to the south and then makes a left turn and starts heading to the north again. They kind of look like the letter U. You can see there's 2 examples of troughs on this globe right there. In contrast, the opposite of a trough is a ridge. And they kind of look like an upside down letter U. Again, they're not vertical, they're north and south. But the wind was heading kind of north and then made a right turn and started heading to the south. Those are ridges, and again, there's 2 examples of ridges highlighted on this particular map. Ridges and troughs will be useful when we're describing meteorological features here, and we have a notation for them. When we want to label a trough on a map, we use a dashed line to kind of illustrate sort of the axis of the, kind of like the, the central axis of like the U shape right there. So see how there's those 2 dashed lines on there illustrating the axes of those 2 troughs? In the same sort of way, for a ridge, we use a zigzag line. Boy, let me tell you what, PowerPoint does not like to draw zigzag lines. I did the best I can here. And you use that zigzag line to sort of illustrate the axis, you know, the reflection or whatever, of those two ridges right there. It's just a notation, but it's awfully useful. Those troughs and ridges aren't just kind of, oh, that's interesting that the jet stream would do that. They're actually a big part of the story of cyclogenesis and how cyclones form and so on. I don't want to get into all the details of it, but they are in fact very much related to where and how cyclones form. On this map here, those, you know, that's showing the jet stream right there. You can see how there's troughs and ridges in the flow. In general, this is, you know, maybe 10 kilometers up or something like that. But down at the surface beneath it, you should expect to find cyclones forming. And in fact, the cyclones form in one particular, the cyclogenesis is happening in a particular place. It's happening between the trough and the ridge, with the trough to the west and the ridge to the east. Okay, they don't happen inside the trough, they don't happen inside the ridge, they happen between the trough and the ridge, but you want the trough to the west and the ridge to the east to be getting cyclogenesis at the surface. Now, in this part of the lecture, I told you all about the midlatitude jet stream and the subtropical jet stream. We didn't do too much with the subtropical jet stream. It's a whole different beastie. There's one other really cool kind of jet, the tropical easterly jet, but it's very much about the story of monsoons, and part 4 of this lecture is all about monsoons. So we're going to put that off for a little while and talk about tropical easterly jets at that time. In the meantime, though, let's answer a couple of questions about jet streams before moving on to part 3 of our lecture. Question 7. Jet streams that we have discussed so far are blank scale phenomena in the atmosphere featuring blank winds. They are mesoscale or are they synoptic scale? And are they westerlies or are they easterlies? Which of those is the correct way of describing the jet streams that we've seen so far in this class? Alright, make a choice from those 4 options and get some feedback before you move on to question 8.